Good morning, dear students. We learn finite element method. Introduction to finite element method. Here we will learn what is the definition of FEM, what are the application of FEM, history of FEM, and its advantages and disadvantages. The finite element method is a numerical tool to define the field variables in a complex situation in a cause component effect system. In almost all the sort of engineering analysis system becomes a complex due to complexity of load, including nature and point of application. Hence, of such situation, designer has take a help of some numerical techniques to get a value of field variables to this to reasonable level of accuracy, which is the best possible with the finite element. This chapter includes the introduction of CAD, comparison with the other methods, its types, steps of in FEM, principle of minimum potential, pre-processor, post-processor, method to solve one-dimensional, two-dimensional trust method. The FEM is a numerical technique to find the field variables. Now, what are the field variables? Displacement, stress, strain. In case of electrical system, magnetic field. In case of thermal engineering, it is temperature. It is important technique that used to CAD mainly for the modification of design part. The field variable is the basic parameter that can be measured, and its derivatives are important for modification of design. For example, displacement field and its derivatives like a strain and hence the stress is very important for the modification of design. Other field variables is temperature in case of thermal engineering, magnetic field in case of electrical engineering, and so on. So the finite element method, sometimes referred as a finite element analysis (FEA), is a computational technique used to obtain approximate solution of boundary value problems in engineering. It is not exact method; it is an approximate method. Simply stated, a boundary value problems is a mathematical problem in which one or more dependent variables must satisfy the differential equation everywhere within the known domain of independent variables and satisfy a specific condition of the boundary conditions. So the CAD has advantages over conventional design as it is a cost effective, time saving, no paperwork, easy modification, versatile, accurate, no need of prototype, means you have no need to fabricate the small items, no optimization capacity is improved, speedy and definite result oriented process. Now, what is the engineer prime objective? To solve the engineering problem, which includes problem formulation, mathematical modeling, obtain solution to the problems. That is prediction of the response of the system. Now, what is the engineering difficulty? Analytical solution to the complex problems are sometimes tedious and cumbersome, and sometimes and mostly impossible. So, we are focusing FEM and CAE solid mechanics perspective. So this is the modern product cycle of the based on the CAE design and what is the FEM in day-to-day life. What is we are saying in the old cycle is without FEM is that is the first is the customer demand, then it goes to the product concept, then it becomes a designer engineer, then if we design engineer made the drawing and drafting, then it prototype model will be prepared, then testing at the lab, then field trials, then modification, and again sent to the market, and then market to the you will get the customer feedback. So you have to wait up to the customer feedback. But here what we are doing, we are taking the at engineering, if we are there are any problems, you can take the feedback and we are immediately modified the product. So you hear the use of FEM here. Now there are the various methods for analysis, that is analytical methods and numerical methods. In analytical methods, exact method, that is separation of variables, Laplace transformation, and approximate method, that is Rayleigh's method, Galer's methods. Whereas in numerical methods, numerical solution of differential equation, which is again divided into two parts, that is numerical integration and finite difference. Where and numerical method again is a finite method of discrete element methods. So analytical methods, this is the example of simply loaded beam. Now this is, you can solve this problem, it is Macleod's method. So you know this method. Then approximate method. Analytical methods are not suitable for a complex problem. The complexity can be due to the geometry, material properties, complex geometry conditions. Hence, the approximate method are used. So these are the methods. I am showing these methods. Then concept. So these are then then finite difference method do. Finite difference method converts the continuum variation problems into the discrete variation problems. The algebraic equation thus resulted are easy to handle and can be solved by generalized method. The governing differential equation is written in a finite difference form, and then using forward and backward or central difference method, values of the field variables are obtained at the nodes using boundary conditions. To find the temperature at a particular nodes of a slab with a given condition of finite difference. Now we have solved this type of problems. If you have to find here the temperature of 600 is given at the one end and other end is 300, again if you want to find the temperature inside the wall, then you have to divide the wall into number of parts and declare here you will get the values at solution at each nodes. So these are the we have solved these problems in first year engineering. Then Rayleigh's method is there. Then other methods are the finite. What finite method is do? Numerical method for engineering. Design of engineering system requires extensive analysis of various engineering problems in the areas like mechanics of solids, structures, heat transfer, and fluid flow. Precise and accurate analysis of these problems can be lead to optimal design of the system. The first step in engineering analysis is to create a mathematical model of a physical system. The idealization of the physical system to a mathematical model requires a certain assumption that lead to a differential equation governing the mathematical model. The solution of a mathematical model predicts the response of the system. The predicted response will be close to the actual response if the system is modeled very close to the actual of minimum assumptions. So this is the boundary problems. We have solved this type of problem in first year engineering. So, in nutshell, the finite element method is a blend of the features of the functional approximation method and the finite difference method. In this, the body is divided into the small elements and the connecting points are called as nodes. The problem of infinite degree of freedom is converted into the finite degree of freedom. The solution is obtained at element level and it is added to get a solution for the complete system. The various steps of the finite explained considered in the mechanics of solid. The history of FEM in 1943, Courant has developed a variational method. In 1916, Turner, Clark, Martin, and Tuff developed the stiffness matrices. In 1960, Clark method of finite element problems. In 1970s, application of mainframe computers is developed. In 1980s, microcomputers and preprocessor is developed. In 1990, analysis of large structural systems. So the development of FEM is the degree of automobile industry, aerospace industry. In the Second World War, it is developed. Then post WW in jets, missiles, space flights. Then need for lightweight structures required accurate stress analysis and parallel growth of the computers. So the application of FEM is in structural analysis, that is stress analysis, that is statics, dynamic and linear, non-linear modeling. Then mechanical, aerospace, civil and automobile engineering. It is also used in a fluid flow, thermal analysis, that is heat transfer, electromagnetic field analysis, soil and geomechanics, acoustics, biomechanics. Then advantages of FEM is irregular boundaries, general loads, differential materials, boundary conditions, variable element size, easy modification, dynamics and nonlinear problems, that is geometric or material. So these are the applications of FEM: linear, static analysis, non-linear analysis, dynamic analysis, buckling analysis, thermal analysis, CFD analysis, fatigue analysis, crash analysis, NVHH analysis, FSI analysis, and many more. So these are the analysis of truss, aeroplane, crash analysis. These are the some examples of crash analysis: plane, tooth analysis, bone analysis in biomechanics, structural analysis of the buildings. This is the analysis of thermal stadium and stadium analysis, structural analysis of stadium, then truss. This is the buckets, fan, aerofoil section of plane, then satellite, engine frames, turbine blades, then crash analysis of truck, chassis, in toys also. So available commercial software available for this FEM is ANSYS, IDEAS, SDRC, Nastran, Abacus, Cosmos, Algor, Patron, Hypermesh, Thread, Dyna 3D. These are the software. These are the application software used for this FEM analysis. Now I am showing some examples of FEM analysis. This is 10. This is application of FEM in biomechanics. This is analysis of strain, stresses induced in the stress induced in the strain. Then traffic accident analysis, airbag, male and female, and while riding the car, what is the impact of steering on the human head, what is the what is the safety of um, seat belt. Then this is the analysis, CFD analysis of water flow. Then the sheet metal analysis. Sheet metal bending, it is bending of sheet and die. Then I already crash analysis of truck. This is solar dryer analysis. This is airflow CFD analysis. This is CFD analysis. So these are the application of CAD. So I am stopping here. This is application. This is all about the application of CAD. You can learn through this. What is the application of CAD, where it is used, and what of the software are used in the